Recording started.
Welcome to IS223's presentation on Week 1 objectives. This Illuminate session is an opportunity for you to learn more about the weekly objectives as they apply to the object-oriented process. So our first learning objective this week is how can we create a requirements document that will describe what the system behavior is at a high level and then translate that to an object-oriented design that is represented with UML. How do we create a requirements document? What does a requirements document look like? How do we analyze the system using these requirements and come up with a good object-oriented design? For the assignment this week, we need to implement the system described in chapters 12 and 13. The scenario is a good one, and we are asked to design software for an ATM system that has several options available to its user. We can see that here in the mock ATM diagram. The user needs to be able to view their balance, withdraw cash, deposit funds, or possibly exit. In order to create a good design, we must first gather requirements that will meet the needs of the customer, aka the bank, and the user of the ATM. If either party is unhappy, we have not done our job right, and our software engineering career will be short-lived. So we start by interviewing the possible users of the system, and we also get feedback from specialists that have been in the field and have worked very closely possibly with ATM machines. Once we get a feel for how the system can be used, we then consult with the customer or bank to see which high-level system requirements will make it into our final system requirements document. This requirements document will then be the contract between the software engineer and the bank in case someone changes their mind. And trust me, this often happens. Keep in mind that this changing of the requirements happens quite frequently in the real world, and documentation is the only way to prevent conflict and resolve cost issues. Now, once the high-level system requirements are agreed upon, typically the company writing the software will then create low-level software requirements that will then ensure all software team members are on the same page and can work in parallel. If one high-level system requirement changes, it may affect multiple low-level software requirements. However, if we are too resistant to change, we may never see repeat business from the customer again. So there's definitely a happy medium here between too many requirements and being too specific. Slide 4 shows us an example of a few of the requirements that have been established for this ATM case study that we see in our book. Please note that they are fairly detailed and describe how the user interacts with the ATM in a fairly specific way. We can see that we need to, 1, display a welcome message, 2, prompt the user to enter an account number, which is 5 digits, 3, prompt the user to enter a PIN, which is also 5 digits, 4, check to see if the account number and PIN number is valid, and then finally 5, display the main menu. These requirements also tell us that if the user PIN is incorrect, we need to go back to step 1 and restart the authentication process. These are only a few of the requirements from the book that will help us get a feel for what a requirements document looks like. Keep in mind that the best requirements are ones that are testable and verifiable. Otherwise, the customer may have a disagreement as to whether or not a requirement has been met. Most of these requirements listed here are very testable. Software actually has a life cycle of its own and tends to go through stages as it progresses from inception to obsolescence. The different stages involved in the software life cycle are 1, analysis. This is when we gather our requirements from the customer and ensure that everyone is on the same page. We have talked about this in the previous slide. Second is the design. This is where UML comes in handy and allows us to make architecture decisions before we ever start coding. Third is implementation. Once we have the design established, we can choose a high-level language, like Java, to implement our design. Fourth is testing. One of the most important steps is unit testing and system testing. We need to make sure that we have regression tests in place so that we can retest any changes that are made in the future. Fifth is debugging. If a failure condition is found, we must debug the software or find the line of code responsible for the error. Once the error is found, a new test should be added to the regression suite of tests to verify its fix. Next is deployment. Once we have working software, we need to decide how it will be distributed and on which devices. Not all devices work the same, and some devices may have more issues than others. So we may have to prioritize our deployment on different devices. And finally, maintenance. Software is never finished, and there will always be enhancements or new features that need to be added. This is where the design decisions from above will start to show their true colors. If a poor object-oriented design was employed, changes are going to be extremely hard to implement, and so will tests. Now that we know the different stages of the software life cycle, there are also different ways that we can address these stages. The traditional way is through the waterfall method, where each of these stages is executed only once, and we start with analysis, and we are basically done after deployment. Maintenance is basically the end product. Once we're complete with all these stages using the waterfall method, we're constantly maintaining the system after that. This makes for a very rigid structure, and most complex government projects utilize this waterfall model. However, the iterative model is an iterative process, and each stage can be run multiple times. This means that software can be released much more often and can adapt to change much better. Commercial software is typically written in this iterative model fashion to adapt to the market environments quickly. Once we have our requirements document, we can proceed to the design phase and start talking about our design specification. The system has two ways that it can be defined. One is the system structure, which defines the system's objects and their relationships. The other is the system behavior, which shows us how the system objects change as they interact with other system objects. In order to show these relationships, we can utilize UML to modify the different system structures and behaviors. Keep in mind that UML 2 has 13 different types of diagrams that we can use. 6 diagrams are related to system structure, while 7 are related to system behavior. All 13 of these types of diagrams are not necessary, but available if needed. There are 6 UML diagrams that are used quite frequently out of these 13 when designing software, and we will be using each type to help us design our ATM case study from the book. The first is the use case diagram that models the interactions between the system and external entities. Next is the class diagram that helps us model our building blocks or classes of a system. State machine diagrams allow us to model the way in which an object changes state. Activity diagrams show us the high-level interactions that objects perform and in what order. Communication diagrams show the low-level interactions among objects in a system. And finally, sequence diagrams show the timing of the low-level interactions with objects in a system. We will be going over each of these different types of UML diagrams and how they can apply to our ATM case study in the next few slides. The use case diagram is useful, and it allows us to see how different actors interact with the system. These actions should map directly to a requirement in the system's requirements document. Keep in mind that an actor can be a person or another system that interacts with our system. Our next learning objective wants us to be able to look at a requirements document and find the different classes and class attributes that could apply to this document. We need to be able to identify the different classes involved just by looking at the requirements. We can also use UML to help us model these different classes. Each class will have a unique set of attributes that we can find in the requirements document. The best way to identify the classes or objects that we need for our system is to list all the nouns that we can find in the requirements document. This is part of the beauty of creating an object-oriented system. Most objects in an OOP design can be real-world objects. Once they are listed, once we list the nouns, go through and cross off those that do not have any significance in the ATM system. For example, the bank is not part of the ATM system. The bank simply wants us to build it. I have done this in the above diagram, and we see that we are left with only the essential elements of the ATM system. Some of the nouns are crossed off, like account number, and will become an attribute in the class later on. Class diagrams are represented with a rectangle divided into 3 parts. The first part shows the class name. The second part shows the class attributes, which have not been defined yet. And the third part shows the class operations, which have also not been defined yet. In class diagrams, you can represent associations by using a solid line that connects the 2 classes. Multiplicity can show us how many objects of each class participate in the association. Role name can show us the role that a class plays in a particular association. Composition is represented by a solid diamond that shows us which class is part of the whole. Aggregation is represented by a hollow diamond and is a much weaker form of composition. Here's a class diagram that shows most of the elements just described. You can see that the ATM has an association with all the other classes that make up the entire system. You can also see that there are composition diamonds on the ATM side of the associations to help further illustrate the composition relationships. Each rectangle represents a class, and the multiplicity can be seen on all ends of the association relationships. All relationships in this diagram are one-to-one relationships. Here is another class diagram that helps us illustrate how the multiplicity values can be used to name the relationships. A one-to-one relationship has a 1 on both sides of the association, as seen here, for instance, between ATM and deposit slot, or ATM and keypad, or ATM and cash dispenser, or ATM and screen. A 0-to-many or many-to-one relationship implies that more than one class can be associated with a single class. A many-to-many relationship is a complex relationship that does not occur that often. Classes have 2 main elements: attributes or data, and operations or behaviors. The attributes to a class can be found as descriptive words in the requirements document. Here is a list of descriptive words found and the nouns or classes that they belong to. Now that we know the class attributes from the previous slide, we can show which class they belong to by using the UML class diagram. Notice how the second section of some of these classes have the attributes defined. We are halfway there defining our new classes. Now all we need to figure out are the different states, activities, and operations defined in the requirements document. In order to help us model the objects, state, and activities, we can use UML state machine diagrams or activity diagrams. Once we know the different states and activities for each class, we can then focus on finding verbs and verb activities in the requirements document to nail down the unique operations needed for each class. We will see this in the next couple of slides. We can use state machine diagrams to help us model the different states reached at a high level for the entire system. This is important because we need to know if there are some unplanned states that we are not planning for. Unknown states are responsible for many security vulnerabilities that are found in the real world, and hackers will take advantage of these unplanned states. Activity diagrams are used to help model the behavior of classes and objects at the lowest level. In this slide, we can see the behavior involved with the withdraw object. Notice that activity diagrams are very much like state diagrams. The only difference is that they show details behind the class instead of the states of the system at a higher level. We can also see that there are several decision points shown in this activity diagram that lead to different flows of logic depending on the attributes of the class. Now that we have our classes defined, we need to define the operations we will use to support the activity and state diagrams that we have created in previous slides. These operations typically take the form of a verb and relate to the classes in our system. This slide shows a list of those verbs and the classes that they apply to. Now we can finally start to see our design take shape in the form of a class diagram. Remember that we created our classes using the nouns that we found in the requirements document. We then found descriptive words about the nouns in order to create their associated attributes, also known as member variables. Finally, we located the verbs in the requirements document and used them to create the operations, also known as messages, within our classes. Here is a figure showing all the classes, attributes, and operations that have been created up to this point. Now that we have a good idea what the operations needed for these classes, we need to figure out if each operation needs a return type or has parameters associated with it. Here's an example of a couple of the classes. For instance, bank database and account class that have had their operations analyzed and the appropriate return types and parameters added. Parameters should be added if there is additional input needed that particular class does not have. Return types are useful for returning information from a particular message or operation. Interaction diagrams are the final step in fully analyzing our object-oriented design. These are needed to help us identify the unique collaborations between objects. One type of interaction diagram is the communication diagram that shows us which particular objects are involved and which messages are being passed. The other type of diagram, the sequence diagram, shows us when the messages are being sent over the course of an activity. The next couple of slides will help us examine these interaction diagrams in detail. Before we can start to create our interaction diagrams, we need to look at all of the collaborations that exist between the classes. We can see that there are 5 main classes that communicate between each other or with the 5 remaining subclasses. Each one of the messages was an operation that was found as a verb within the requirements document. Keep in mind that if the requirements document is vague, you may need to create a new collaboration message that is needed to support the collaboration between the classes. Once we think we know most of the collaborations needed for our design, we can start to focus in on each activity and their associated communication diagrams. This will ensure that we are not missing any messages or classes needed to complete the required activity. The figure shown here is the balance inquiry communication diagram, showing the messages sent between classes to retrieve the user's current balance. As we can see here, the first message sent is the get available balance message sent to the bank database, who then sends that same message to the account class. And then that message value is returned to the balance inquiry. Then we move on to number 2, which is the get total balance, who is passed to the bank database. The bank database then passes that same get total balance to the account class, and the account class then returns that total balance to balance inquiry. Once that occurs, we can run step 3 and display a message on the screen using the screen class. So the communication diagram works well in showing us which messages are used and in what sequence. Next, we have a sequence diagram showing us the withdrawal activity. Notice that we can see when each message is called and in what order. Each class is a dotted line that represents the object's interface. This diagram is important and allows us to see a very detailed description of how each activity will take place, as well as the different objects and messages that are involved. Last but not least, we're going to talk about polymorphism and inheritance. These are 2 of the most important features that are available within object-oriented programming languages. Inheritance allows us to generalize classes so that we can have a common base class with common attributes and operations that the child class will inherit. Specialization allows us to create a new child class with existing functionality from the base class or parent class. Then we can specialize it for a particular purpose. An example of inheritance and specialization will be shown in the next couple of slides. In the top diagram, you can see the 3 preliminary classes that we have come up with for the ATM case study described in the book. If you look closely, you will see that all 3 classes have an account number and an execute operation. This implies that these 3 classes should have a common base class. In the second diagram, you will see a new base class called transaction that has been factored out and includes the common account number and execute operation elements that were redundant in the other classes above it. We can then extend the transaction base class to specialize and create the other classes. Now there is not redundant code involved for the account number, and all transaction specialization classes have a known execute command that is defined by the parent class. Let's take a look at all of our hard work in the complete class diagram shown. We can see that everything revolves around the ATM class. Deposit slot, keypad, cash dispenser, and screen are classes that allow us to interface to the physical hardware of the machine. The bank database is used to access and modify the account balances of the customer, which may contain 1 or more accounts. The ATM also executes several types of transactions: withdrawal, balance, and inquiry. Finally, let's take a look at all the class names, attributes, and operations. The plus and minus signs next to the class members represent visibility. One with a plus sign are public members, while ones with a minus sign are private. Typically, all attributes are private in order to help encapsulate the data and force a decoupled architecture where no one class is dependent upon another. Encapsulation is another key object-oriented feature that helps with testing and data validation. I hope everyone enjoyed the presentation. Please email me if you have any questions, and I look forward to working with you. Thank you very much.